So in this slide we make the link between the eigenvalues and the modes of the system. So this is the state equation, and what we'll consider here is the unforced state trajectory. Well, this is the same as, well, taking a command, a control that is 0, and we only consider the homogeneous equation. And we had seen that the solution of this homogeneous equation was e exponential of a t minus t0 x0. But here, since we are working with linear time invariant systems without loss of generality, you can say t0 is equal to 0. So this is how we obtain this equation here. And we have just seen that you can rewrite the exponential of at as v e to the lambda t. Lambda is the diagonal matrix with the eigenvalues on the diagonal times v minus 1 x0. V minus 1 is a matrix times x0 is a vector. So alpha here is a vector, alpha 1, alpha n, and it takes into account, of course, the initial conditions, right? So we can say that x of t is v, this is v, and remember that v is constructed of the eigenvectors. This is e to the lambda t, and this is alpha. So if we compute this one, matrix times a vector, this will be a vector, so we'll end up with alpha 1 e to the lambda 1 t, alpha 2 e to the lambda 2t, etc. up to alpha e to the lambda n t. Okay, so here we multiply a matrix with a vector, and we've seen in the activity linear algebra and applications that, well, the result will be, of course, be a vector, but it will be a linear combination of the columns of v. Remember that the columns are the eigenvectors, and this linear combination comes from the elements that you have in the vector. So you can rewrite x of t in this fashion over here. Okay, and this is in the case where all the eigenvalues are distinct, right? And you can see that this, well, unforced state trajectory depends on the eigenvectors, the eigenvalues, and the initial conditions. So in summary, the enforced state trajectory is given over here. It depends on the initial conditions, the eigenvalues, and the eigenvectors. So the evolution, the unforced evolution of the system, it will also be the case, of course, for the forced evolution, depends on the eigenvalues lambda I through the modes of the system. So this is called the mode of the system, and we say that this mode is excited if the corresponding alpha I is different from 0. So remember that we can write this if A is diagonalizable. If this is not the case, okay, if A is not diagonalizable, you can still write x of t is equal to e to the exponential of a t times x0. But if you do the calculation, you'll have to work with these Jordan blocks and things like that, so things become a bit more complicated, and you can obtain expressions like this one, but it will also involve, well, modes that take this form. So you'll have e to the lambda I t, but you'll have t to some power, that depends on the size of your Jordan block, t to some power times e to the lambda I t. We'll illustrate this in an example later on in the course. So in this slide you can see that the number of eigenvalues is m, which is smaller than n. A here is in Rn times n. There are n states. Since m is smaller or equal to n, it means that some eigenvalues can have an algebraic multiplicity higher than 1. Let's say, for instance, that lambda 1 is equal to -1 and that it has an algebraic multiplicity of 3. So this means that, well, -1 is eigenvalue 3 times, and in this case we'll have a mode e to the lambda t, which is e to the minus t, right? But you'll also have the mode t e to the minus t and the mode t square e to the minus t. Okay, but what is really important, you see, is that the real part of the eigenvalue is negative, which is the case because all mode types will be decaying, because, well, the exponential here will win over these polynomial functions of time. Okay, so what is really important is that the real part of the eigenvalue is negative. Well, the natural response, that's the unforced response of this state equation, is shown over here, and, well, the stability of this equation depends only on the matrix A, because we've just seen that the solution of this, well, depends on the modes e to the lambda I t, and these here are the eigenvalues of A. So we can therefore speak of the stability of an LTI system with a realization A, B, C, and D. And it's obvious from what you see over here and the modes that you've got here, that if the eigenvalues of A are lambda 1 up to lambda m, okay, well, the corresponding system here with state equation shown over here is asymptotically stable if and only if all these eigenvalues are such that they have a real part that is negative. Okay, so that you would have complex exponential that are decaying, right? If there is at least one eigenvalue with a real part that is larger than 0, then the system is unstable. We have seen this in previous courses, but the stability, of course, depends only on the real part of the eigenvalues. And as stated before, the eigenvalues here are really the poles of the system. We can see this because, well, if you have a mode, okay, with lambda this complex, a complex quantity, well, you can write, well, the magnitude of e to the lambda t, so that's e to the aib times t, of which you take the magnitude. Okay, this thing can be rewritten as e to the at times e to the ibt. You take the magnitude, and this results in this quantity over here, because this is always positive, right? And you know that this is living on the unit circle, so its magnitude is, of course, always 1. Okay, so you see here that the magnitude of e to the lambda t, the mode, does only depend on the real part of the eigenvalue. So this is the LTI state space description that we've encountered previously in the course with the initial condition, and we have seen that you can find the solution of this dynamical equation, but very often it's easier to work in the Laplace transform, as we have seen in the course of signals and systems. So what you can do is go to the Laplace domain, so you'll take both equations and you apply the Laplace transform. Okay, so here we have to apply the property of the Laplace transform of a derivative. So it's s times the Laplace transform of x, which is x of s, minus the initial conditions. Well, for the other signals, we simply take the Laplace transform. The Laplace transform of x of t is x of s, and the Laplace transform of u of t is u of s. Okay, so what we can do is reorganize things, because we have x of s here and x of s here. So we have s times the identity matrix minus a times x of s is equal to x0, okay, we take it to the other side, plus b u s, right? So this means that x of s can be written as s I minus a inverse times x0 plus s I minus a inverse times b u s, right? This equation stays the same, and then you can inject, of course, the solution of x of s in here, and you obtain the solution or the output equation in the Laplace domain. This quantity here we have encountered when we were computing the exponential of a t, right? Remember that we had to take the inverse Laplace transform of si minus a inverse. So this is what we had computed in the previous slides, and here you have the result of the output equation. Remember that we had y of s is c x of s plus d u of s, and if you inject this one in here, this is what you obtain, right? And now we can obtain the transfer matrix of the system, and the transfer matrix is the relation between the input and the output when we have initial conditions that are zero. So if the initial conditions are zero, this term over here disappears, and the relation between us and ys is this quantity over here. So this is how you can compute the transfer matrix of a system, and this quantity you should be able to find it back so that you can compute a transfer matrix of a system. So please don't learn it by heart, just go through the procedure that we have just done. So we can apply this to the LCL filter that we had considered before. Okay, so this is the LCL filter. We have L1 over here, L2. Well, the input is, well, slightly different in notation, Vinf, and you'll see in the teaching unit commande et interfaçage de système électrique why it's Vinf and why the output here is Vgrid. This current here is Einf, and the current here is E-grid, right? And the capacitor is C over here. We have done an exercise where we have found the matrices A, B, and C. C here is 1, 0, 0, 0, 1, 0. So the state vector in this case is E-inf, E-grid, and VC. So apparently here we are only interested in Einf and E-grid. Okay, so this is why we have a matrix with two rows over here. And if you compute C times S I minus A inverse times B, and you can do this in Matlab using the symbolic toolbox. It will do all the hard work for you, and then you simplify, you will see that you come up with the transfer matrix, and this comes in handy if you analyze systems. Well, remember that the state space representation is non-unique. If this is a realization of the system, okay, this is the state space description of the system, well, then you can take any non-singular matrix that is in Rn times n, and you can construct as many other realizations as you want. But what we will see is that the transfer function, or the transfer matrix in this case, does not depend on the realization that you've chosen. We have just seen that the transfer matrix can be written like this. Okay, this is using this realization, and you should obtain the same result if, well, you replace C by Ct, A by T minus 1 AT, and B by T minus 1 B, right? Well, what you can do here, the identity matrix, you can write it as T minus 1 T, right? So that you can go to this expression over here. You have T minus 1 and T minus 1, and here at the end you have T and T. So this expression over here, you can rewrite it as this expression. So now we're going to use this expression here, so maybe we can show where it comes from. So T minus 1 x T inverse is obviously equal to T minus 1 x T inverse. Okay, so remember that if you have A, B, C inverse, this is equal to C minus 1, B minus 1, A minus 1, and this comes from the course on linear algebra and application. So if we do this over here, we'll have T minus 1, x minus 1, and the inverse of T minus 1 is T, and this is equal to T minus 1 x T minus 1. So now I will pre-multiply with T and post-multiply by T minus 1, and we'll have this relation over here. Okay, so this is indeed correct. And if we apply this relation in this last equation with x is equal to Si minus A, we see that this thing over here is equal to Si minus A inverse, right? So we see that, well, whatever the realization that you've chosen, whatever the T that you've chosen, the transfer matrix remains the same. So in this slide, we go from a transfer function representation to a state space representation, and we do this in the single input, single output case. In the multivariable case, this is much more complicated, and this goes beyond the scope of this course. In the multivariable case, you arrive at a state space representation as we have done before through modeling and linearization. Okay, so suppose that you're given a transfer function and that it is proper but not strictly proper. What you'll have to do is to do a Euclidean division, okay, and so you'll end up with a constant and another transfer function h of s, the one that you're working with is h bar here, and this h of s will be strictly proper. This term over here, this constant, will be the direct feed through term. As you know, I've said it before, most physical systems do not have a direct feed through term, so you'll end up with a transfer function that is strictly proper. So from now on, we'll work with a strictly proper transfer function h of s that has this form over here. So what we'll do is bring this transfer function, which is strictly proper and can be written as a polynomial b over a polynomial a. The polynomial b is given over here, that's b. It's a polynomial of s, and here at the denominator we have a. right? And what we have written is y of s is b s us, no, not us, vs is 1 over a us. And if you plug this in here, you have ys is equal to b, polynomial b over polynomial a us, and this is h of s, right? Using this relation here, you can write Sn Vs. This is obtained by multiplying by As, so that you have an As appearing on here. The Us will go over there, and then, well, you keep the first term on one side and you take the other terms on the other side. So you'll have minus a1 Sn minus 1 up to minus an, the whole thing times Vs plus Us, right? This we'll be using later. So what we'll do is find the realization, where of course you have x dot is equal to a, and then we have x over here. And as stated here, x will be the signal v. This is x1, x2 will be v dot, and xn will be the n minus 1 derivative of v. Okay, so obviously x dot will be v dot, v double dot, up to the derivative, the nth derivative of v, right? So now it's rather easy to complete the matrix A, at least the first n minus 1 rows, v dot, so we have a 0 here, 1, and then 0, and all 0 up to there. Here we have 0, 0, 1, up to 0 over here, and the line n minus 1, we have zeros everywhere except here at the end, right? Now we'll use this line over here, okay, to fill in the last line over here, because this is the nth derivative and this is the nth derivative that we have on this side, and on the other side we'll have, well, the minus a1 times the n minus 1 derivative of v. Okay, so I'll have minus a1 over here, right? And here at the beginning, well, I have minus an vs, but that's the first state. So here I have minus an, and you'll have, of course, minus an minus 1, and so on. So this is the matrix that you see over here, okay? And of course here I have to complete, because I have my matrix B over here and my input, yeah, which is of course U. I have zeros everywhere except in the last line, and this is coming from this one over here. So this is indeed the B that I've got, right? So now I have my state, but I'm interested, of course, in the output, right? But you can see that the output is y is equal to b as v, right? And b is given over here. So it's b1, the n minus 1 derivative of v. Okay, so my c, here it's transposed, will have to select b1 times the n minus 1 derivative. Okay, and of course, then you go in the other side. I have b2 times the n minus 2 derivative, so b2, and up to bn times v, and v is the first state, so this is why you've got it over here, right? So this is indeed my c. So this is how you can bring this strictly proper transfer function, right, with two polynomials b over a, where b is here and a is over here, in a so-called controller canonical form. So this is one way to see things. Remember that we are, well, implementing this transfer function, this strictly proper h of s. Remember that we had seen that, well, Sn v of s, right, is equal to minus a1 Sn minus 1 minus a2 Sn minus 2 minus up to minus an, that's times vs, right, plus us. So what you've got here is the nth derivative of v, right? This is what you've got here. It's us, this is this one, minus a1 times the n minus 1 derivative. Okay, if you integrate one time, you have vn minus 1 over here. If you have integrate another time, you have vn minus 2. And if you keep on integrating, what you will have here is v, right? So this equation is implemented by this operation here. So this is vn, this is what is given over here. It's us and then minus a1 times the n minus 1 derivative minus a2 times the n minus 2 derivative up to minus an times v. Okay, so this equation, you can see it over here. The output was given by y of s is equal to b1 Sn minus 1 plus b2 Sn minus 2 up to bn times vs, right? So the output is constructed by all those terms here. It's b1 times the n minus 1 derivative, yeah, plus b2 times the n minus 2 derivative up to bn times v. Okay, so this is y is constructed. So this is how you can implement this transfer function, okay, this strictly proper transfer function of which the transfer function was given, and you need, of course, n integrators. Well, as you might have noticed, I have skipped a few slides that are there for your information, and those slides contain, well, the controllability canonical form, the observer canonical form, and the observability canonical forms. Those are different canonical forms that can be used to implement the transfer function h of s that you see on the screen. Well, one form that is important is the so-called modal form, and in this slide here we assume that we have distinct poles and that the poles are simple poles. Okay, so if this is the case, we can rewrite this transfer function, and this will of course involve a partial fraction expansion. You can rewrite h of s in this form over here. So we have that y is a sum, okay, of I going from 1 to n of ci over s minus pi times u. Okay, so we'll define the states as follow. We'll say that the states are 1 over s minus pi u. Okay, so that you can write y as a sum of E is equal to 1 to n of Ci xi. Okay, so this is explaining why my C matrix looks like this one, right? So this one you can rewrite as S minus Pi xi equals U. If you take the inverse Laplace transform, you'll have dxi over dt minus Pi xi, and I'll take it to the other side, Pi xi, right, plus U. Okay, remember that my states are x1 up to xn, when I will have so this is the state x, I will have x dot here, and this is the A matrix. Okay, I have here plus something U. Okay, so obviously here I will have x1 dot, x2 dot, and so forth up to xn dot. And you can see from what I've written here, because this is xi dot, okay, that I will have here p1 0 0, and on the diagonal I will have p1 p2 up to pn. Each time I have to add U, so I have a 1. So this is a vector of ones, and this is the B matrix, and so this is indeed how you obtain the B and how we obtain the A. The A is a matrix. Since the system here is a single input, single output system, well, B and C are vectors. Okay, so this is why I use here lowercase letters. So this is the implementation that you have in the case of distinct poles when you use this modal form. Remember that this equation here implements simply x1 dot is U plus p1x. Okay, so you have this for every single system, and then you simply have to x1 is the state, x2 is the state up to xn, and then you have to take the linear combinations of the states using the coefficient c1, c2 up to cn. So suppose now that we have multiple poles, and in the case of multiple poles it's impossible to do it in a general case, so I'll take an example over here. So suppose that, well, all poles are simple except P1, that is a triple pole, so that when you do the partial fraction expansion you end up with something like this as far as the first pole is concerned. So if we put this in a state space format, what we'll do is, well, say that the third state is 1 over s minus p1 U. The second state will be 1 over s minus p1 squared U. So this means that x2 is equal to 1 over s minus p1 x3, right? And x1 will be 1 over s minus p1 cube U. So this means that x1 will be 1 over s minus p1 x2, right? And of course y, as usual, will be c1 x1 plus c2 x2 plus c3 x3 and so on. So this is why you have a c that takes this form over here. Well, if this is the first equation, this is the second equation, and this is the third equation here, we've seen before that you can rewrite the first equation as s minus p1 times x3, which is u, and if you take the inverse Laplace transform, what you'll obtain is, well, x3 dot is equal to p1 x3 plus u. Okay, you can do something similar for the second equation, and you'll have x2 dot is equal to p1 x2 but plus x3. Okay, so we've taken this relation over here, and the third equation here will yield, well, x1 dot is equal to p1 x1 plus x2. Okay, so these are the three important relations. Okay, so where do we have some place here? So let's write as usual x, so this is x1 up to xn. Here I'll have to construct the A matrix, and this will be x dot, so we have x1 dot, x2 dot, x3 dot up to xn dot, right? And we have to add, of course, the B matrix times the input. So let us take this equation over here, the third equation. What do we see? x1 dot is, well, p1 x1, so this means that we have p1 plus x2, so we have a 1 over here, and then all zeros. The second equation will be this one over here, x2 dot, this is p1, sorry, x2, so 0, p2 plus x3, 0, 0, 0. The third equation here, there's this equation over here, x3 dot is, well, it's not p2 over here, of course, it's p1, 0, p1, 0 plus u, so here we had zeros, zeros, and here we have a 1. Okay, and for the other states, well, it's as before, so you have on the diagonal the poles and zeros everywhere and ones that are coming. So what is important to see here is that you have this Jordan block that is appearing. This Jordan block looked a bit strange, okay, but now you can see that it comes from the multiple poles as we could expect, right? So this is how this Jordan block is appearing, and when you have Jordan blocks, multiple poles, as I've said before, well, you have modes that are different. Well, this one will give a mode of the type exponential of p1t. This one, if you take the inverse Laplace transform, will give modes of the type t exponential of p1t, and this one will produce modes of the type t squared over 2 exponential of p1t. So as announced before, this is an example where you have multiple poles, yeah, in the transfer function, and when you construct a realization, a state space description, you end up with a Jordan block in your A matrix. And when you have multiple poles, right, well, this means that you have other modes than just exponential of p1t. You have these two in this case, because we have this pole is of algebraic multiplicity 3. You have these two modes that are added. So these are the relations between the different model representations in the case of single input, single output systems. You know that the system can be described by a differential equation. Okay, it will be scalar in this case because the system is a single input, single output. Well, by going to the Laplace domain, well, you can compute the transfer function. Okay, we have just seen that if you're given the scalar description, you can obtain the transfer function, but using the transfer function you can obtain also very easily the state space description from the transfer function or from the differential equation itself, right? And well, if you take the Laplace transform of this one, you can see that you can compute the transfer function from the matrices A, B, C, and D, and this will yield something that is of course equivalent than what is given by this transfer function over here. So far we have considered continuous time linear state space description, but if we sample the signals and we consider regular sampling instance t is equal to kts, where k is an integer, we obtain, well, descriptions, discrete time state space descriptions, which are really linear difference matrix equations, as we will see. So we'll discretize the system, and as usual, instead of writing u of kts, we'll use a shorthand notation u of k. So another reason why we're interested in discretization is because we are going to design state space controllers and observers in this course. And of course we would like to implement these on a processor, right? So what we could do, for instance, with the observer is simply discretize the observer and see what happens. But we will see in the course of digital control that this is not a very good strategy, because we do not take into account the zero order hold that is inherent to sampling in our design. So a better approach is to take the continuous time description and use a ZOH discretization method that will capture this zero order hold dynamics. Okay, so we'll end up with a model that will be discrete and that will have this form. And it's a better idea then to do the design of the state space controllers and the state space observers on this discrete design that captures the effect of the zero order hold. So how can we do this discretization? Remember that the overall solution of the state equation that we found previously is given over here. Okay, where t0 here is the, well, the time at the initial condition, right? So what you can do is rewrite this at the sampling instance. So in this case, for instance, t0 in this equation here, t0 is 0, and we have replaced t by ts, right? In this case here, t0 is equal to ts, and t is equal to 2ts, and so on, right? So we end up with this equation here, we know that we can rewrite this differently. So it's x of k plus 1 is equal to this matrix here, the exponential of a ts. This is why we have spent so much time on the exponential of a t, right? So that we could compute this quantity over here, xk. This will be my state transition matrix in discrete time. This is what we'll call AD, and here we have a term that we'll call u prime of k in the next slide. So this is a summary of the previous slide. We arrive at a matrix difference equation, okay, that is over here. And the matrix that is over here that we'll call AD is the transition state matrix. So far, we have said that the influence of the input comes in the form of this u prime that is defined over here. So now we are going to introduce the fact that we are using a zero order hold, and when we use a zero order hold, then the inputs are maintained constant between sampling instants. Okay, so ut is equal to u of k, which is u of kts. This is the shorthand notation, right, in the interval from kts to k plus 1 times ts, right? So since it's constant, we can take it out of the integral. Okay, so this is why we have this parenthesis here. So what we'll do now is rewrite this, and we'll do a change of notation, right? So this is sigma over here, right? So if you take the derivative on both sides, you will have d sigma is equal to minus d tau. Okay, so this integral, you can rewrite it as an integral. Because of this one, we have a minus here, and we'll have a d sigma. This is simply rewriting d tau as minus d sigma. Okay, so here we'll have the b, and we'll have the a exponential of a sigma, right? And then we have to look at, well, the integration limits. And well, here the lower limit, if you plug tau is equal to kts in here, you'll have ts, and if you plug tau is equal to k plus 1 ts, the upper integration limit will be 0. Okay, so times uk, this is equal to u prime k, right? But this thing here, you can rewrite it as follows, and this will play the role of b of d. So this is the control matrix in the discrete time case. So we arrive at the following discrete time state space description of the system. So this is the state equation. This is where you have the dynamics. Remember that AD is constructed as follows, and BD is constructed as follows. Well, the output equation, it's a static equation, does not change. So this is why the C in discrete time is equal to the C in continuous time, and you have the same thing for the D matrix. So what we can do is compute the transfer matrix. We assume here that there are no initial conditions. Okay, anyway, for the transfer matrix, we look at the relation between input and output in the case where the initial conditions are 0. So we have to go to the z domain. So we take this equation over here. So we have z x of z is equal to AD x of z plus BD uz. So this we can rewrite as z times the identity matrix minus AD times xz is equal to BD uz. So xz is z times the identity matrix minus a inverse times b d u c, right? And if you plug now this relation in the relation yz is equal to c d, it's d of course here, x of z plus d uz, you'll end up with this transfer matrix over here. Okay, so again, this is something that should be able to use and find at the time of the exam. So here's a summary of the discretization procedure. So here is our continuous time process. Here is the analog to digital conversion using this sample hold system. And here we have our discrete input. So we have the digital to analog conversion. As you can see, we use here a zero order hold system, right? And if you take the relation between the discrete input to the discrete output, we have just computed that this system here in the dashed box can be described by this relation over here. Remember that a of d can be constructed from a as exponential of a ts. Ts here is the sampling period, and b of d is the integral from 0 to ts of the exponential of a sigma b d sigma, right? So we have a ways of going from the continuous time state space description to the discrete time difference equation, right? And if we use this representation in the design of our discrete time state space controllers and observers, we take the zero order hold into account in our design, and as we will see in the course of digital control, that's a very good thing. Very quickly, I'll give you an overview of the commands in Matlab. So have a look at the slides and also have a look at the documentation. So here, this is how you can enter a system in the form of a zero pole format. You can also use a transfer function format or a state space format. Of course, you'll be using this format quite a lot. You can use format conversions. So for instance, go from zero pole to state space or to transfer matrix. Well, you can do frequency responses, simulations, impulse step, simulations to any type of input signal, and of course you can do discretization, and the command C to D is a very important command. If you use simply C to D, you'll use the correct way of doing the discretization using the ZOH method that we've introduced in the course. So let's do a little exercise on writing state space descriptions and obtaining the discrete time version of those state space descriptions. So we'll take a double integrator, okay, and in order to obtain the state space description, we can write the system as follows. So we say that x2 is 1 over SU. Okay, so this is equivalent of saying x2 dot is equal to u, right? And we'll say x1 is 1 over s x2. So this is equivalent of to saying x1 dot is equal to x2, right? So here the output will be y is equal to x1, and this is 1 over s x2, but x2 is 1 over s u. So indeed what we're going to implement is 1 over s square u, right? So what we'll do is use these two equations here, right, to obtain the state space description, right? So we'll put the state in here, x1, x2. So here will be our matrix A, and x1 dot, x2 dot, this is x dot, this is x, and here we have B, and here the input, right? So if we look at these two equations over here, well, let's take the second one. x1 dot is equal to x2, so x1 dot is 0 times x1 plus 1 times x2, and there is no influence of u. This is coming from this equation. If we take this equation over here, x2 dot, so this is a 2 over here, x2 dot is equal to u, so we have a 1 over here and zeros over here, right? And we can write the output y as simply selecting x1. So we need a 1 and a 0 over here, and we can forget about the direct feed-through, which is 0. Okay, so this is the continuous time state description. So what we can now do is go to discrete time. So what we'll need is the exponential of at, right? And this is this example here where you can use the definition, which is identity matrix plus a t plus a square t over 2, etc. But this one will be 0. If you take this matrix and you multiply it by itself, you'll obtain the 0 matrix. Okay, so what we'll have here is 1 0 0 1 plus 0 1 0 0 t. So the matrix is simply 1 t 0 1, right? So we know that the discrete time state space matrix or state transition matrix is the exponential of a times ts, where ts is the sampling period, so it will be this matrix here. Right, for BD, well, this is the integral from 0 to ts of the exponential of a sigma b d sigma. So this is the integral from 0 to ts. So we'll write 1 sigma 0 1 times b 0 1 d sigma. So this is the integral from 0 to ts of, well, sigma and 1 d sigma. So this is equal to sigma square over 2 sigma evaluated at 0 ts. So we obtain ts square over 2 ts, right? This is bd, and this is ad over here. Of course, C D is equal to C, and it's equal to 1, 0. Right? So what we can do now is also compute the transfer function here, because we have a single input, single output system. So it's CD Z times the identity matrix minus A inverse times BD, right? And need to take this matrix over here. So ZI minus AD inverse, this is, here we'll have Z minus 1, we'll have minus TS, we'll have 0, and we'll have Z minus 1 inverse. So it's 1 over the determinant, Z minus 1 squared, right? So we switch these two, and we have to change the other two of sign. So we have Z minus 1 TS 0 Z minus 1. So H of Z is 1, 0, okay, times this matrix here, 1 over Z minus 1 squared, Z minus 1 TS 0 Z minus 1, and now we have to multiply by the discrete P matrix. Okay, so let's first do this multiplication over here, because that's the easiest. We'll have, well, 1 over Z minus 1 squared, right? And then we'll have Z minus 1, and we'll have TS, and this we have to multiply by TS squared over 2 TS. So we'll have 1 over Z minus 1 squared, okay, then we'll have Z minus 1 times TS squared over 2 plus TS squared, right? And so this means that we have TS squared over 2, right, over Z minus 1 squared times, so we have the Z plus 1, okay, and this is H of Z. So this is the discrete transfer function of a double integrator that has been discretized using the zero order hold method.